a cross section of like a piece of what do you say, watermelon? Really thin watermelon. You see, it's like really thin, so you see it like two-dimensional. So if we spin it around right here, let's see, watch. If we're gonna spin it, it's gonna create this. You like see it, no? It's a watermelon where we cut out, and right in the middle we cut out that, and then we still got some watermelon there. So it's a washer, no? Let me see what I was gonna see over here. Show you. What they call it is a washer. Well, this is called a washer, no? You guys know this is called a washer? So that's because it's solid around it. It's a ring. So this it got took out. So it's hollow. So what you need to know is that it is hollow. It is not like over there where we done that cone over there. The cone is not hollow. The cone is solid, no? So that's what we got to do. So how do we come up with the formula for it? Okay, let's see. How can we come up with the volume of this? Let's see. Let's do. So the volume is going to equal to basically, what is it going to be? It is pi, and then you got the radius squared, and then let's say it's dx. And it's going to go from what to what? See, the difference between this one and the other one is that you actually are going to subtract another volume. So you got to remember that they're going to have to be separated, no? And that would be a different radius. So that's kind of like the idea here. Let's do this. So go back to this. Let's go back to just the cross section. Okay, we're going looking back the cross section of it. It is from A to B, I guess. We go from A to B. Okay, it is pi r squared dx, where this capital R is the outside one, which is the from the center all the way to where the green part of the watermelon. What is that called? The green part of the watermelon.
The rind.
Oh, is it the rind? Okay. So to the rind. I didn't know that. So yeah, to the, that's capitalized, minus the inside. So the volume of the outer function, and basically, wouldn't it be like the whole thing? Then it would be a watermelon that it would just cut in half. No, it has completely everything.
Hi, if the student isn't here, can you send the pass back to room 108?
Mm-hmm.
Thank you.
So it's basically, let's say that this watermelon, which is completely cut in half, and we got the watermelon still, we haven't done anything to it. And so now we're going to subtract that was took out. So now we're going to subtract separately, no? From A to B, the inside, pi r squared, the inside radius. And that's the inside radius. They are separated. So one big thing to remember on the difference between what was the other one? The disk method. The disk method was just that it's not hollow. It's the whole thing. So when it's hollow and it has something missing in the inside, you got to separate the two. Is it necessarily you have to separate them? Well, not necessarily again. Why? Because we could kind of connect it together. This is the same as this, so we could do it like this also. Look, A to B, and pi, and then go r of x squared. Okay, the whole thing, and then minus. We factor out the pi, r of x squared, and then the whole thing dx. We could actually do this. Yes, we could actually do that too. In any case, just know that volume of this outer function minus volume of the inner function. In this graph, we got r of x is this square root function. The right, you guys say is the right, is the outer one, and the inside is the quadratic. And so the volume of this particular one, when we spin it in, around that, whatever that is, if it's the x-axis, we will go from 0 to 1, say that they do intersect here at x is 1, and then at 0 here. And then it is going to be pi square root of x is the outer one, minus, and if we want to separate them, again, if we want to, we don't have to, you know, like I was doing, we could do it this other way. In the inside radius, it is going to be x squared. And so there's that. Let's see if what I'm saying is true. Get your calculators right now. This is you get your calculator, and give me the answer to this particular one. What is the answer to this? And then what is the answer to what I just said it is equivalent to? I'm saying that it is also equivalent to v from 0 to 1, and I'm saying that it is pi. Did I factor it out? Yes, they both have pi. Then I'm going to go with square root of x. The quantity, that's the radius, and you're going to square it, minus, I factor out the pi, then you got x squared squared, and then the whole thing dx. So now, let me see if they are the same. Do it the top, well, how it's written in the top here, and then if it's the same answer as what I've written here, and they should be the same, no? What you guys getting for the top one? 3 pi by 2? 10 pi by 2? 3 pi by 10. Why don't we do it for this bottom one? Let's see if it does turn out to be the same answer or not. And you could actually even factor out the pi again. But in any case, let's just do it like that. Is it or is it not? Is it? Please be. Is it or is it not? Yes? Look, at the end of the day, I don't know. Look, at the end of the day, this right here, the most simplified you can think about it here is that the volume equals, when it's a washer, volume equals pi. You could factor out the pi, integral from a to b, whatever those lower and upper bounds are, and then subtract the difference between the outer and the inner function, but it's pi r squared, so each one of them got to be squared, and dx. And then if you revolve it around the y, then everything turns out ry r of x dy. That is the lesson for today, basically. That's it. What is this now? Volume washer revolving around other axis. Whatever. In this graph, the equation of the outer function is y equals x squared. The graph of the inner function is y equals square root of x. The area in between is revolved about the line y equal to 2. So if it's revolved around this is y equal to 2. It goes back to pre-calculus one more time. It's just pre-calc. And if you do know how to shift functions, then this is not necessary again. It goes back to what I just simplified. It would be v equals, and it would be the same answer, no? V equals pi. It's still going. You can move it back to this one here by subtracting 2. Yes, because as it is, okay, hold on. It's revolved about y equal to 2, so it's going to create this. Look. Let me revolve around there. See what kind of shape does it create. Watch. Revolve around, because this is not y. Did I say y? Yeah, this is y equal to 2. This is y equal to 0. Yes. So we're going to revolve it around here, not here. So it's going to create a different shape. Watch. So it's like a bowl. It's like a bowl like you put to the side that has a hole all the way through here. So it's like, yeah. So that's the kind of shape you got here. So what's the volume of this shape? If you could see it, it's like a saucer. I don't know. So how do we do this? So the volume would be. Let's go back to the graph. Yeah, let's go. Let's see. So it's going to be pi, and then the outer function is, what's the outer function? The outer function is, what's the outer function? Would this be considered the outer function? See, this is, remember when we talked about last time that this is the inside, so this is considered outer, this is considered inner. So if this is the outer function, so let's go. The outer function is what? What is this? X squared. Minus the where it's revolved around. That's what it is. It's the outer minus this. So it's going to be what? X squared minus what? Minus 2. And then minus the inner function minus wherever it's being revolved around. So what is this? Square root of x minus where it's revolved around. And it's dy. Hold on, we got a problem. What is this? We're doing this, no? We got a problem. Because we're doing dy or we're doing dx? We're doing dx? We're doing dx, no? We're doing dx because it's this minus that, and we're going dx. Okay, so this is dx. But it's put that in a calculator. Put it in a calculator. Let's see what are we getting with this. Oh, it's no, it's still, because we're doing dx again. This is 0 to 1 still. What are you guys getting? All right. Look, I have another proposition here. Let's do another proposition. Just for you guys to really understand, and is this gonna work? What I'm gonna say. What if we do instead? We do dy. If we do dy, can we do dy? So if we do dy, 31 pi over 30. If we do dy, okay, these rectangles are gonna go from the bottom to the top. So say this is dy. And then we got volume equals pi. And it's gonna go from 0 to, what is this? Is this still 1? Huh? What is this? If we go dy, what is this? Is it still 1, isn't it? Because it doesn't matter, because if x is 1, yeah, it's 1, no? Yeah, it's 1. So it's still going to go from 0 to 1. Can we do it like this? I'm just asking, can we do it where we have dy? If we do have dy, it would be what? This is still the top, isn't it? No, this is going to be the top minus the bottom. But everything has to be in terms of what? In terms of dy, no? So if this is the top, and that's y equals what? X squared? We have to solve for x. So then this becomes square root of y, isn't it? You see it? So this is going to become the integral of square root of y minus what? Minus and this is what? This is the inside, where this is what? So what? Y to square root of x? But everything has to be in terms of y, no? So what is this going to become? You see how weird this whole thing, it works out just the same. So this is going to be what? Y squared minus? And then let's see if that's the answer. Let's go if we get the same answer. It should be the same answer. I hope. It turned out negative? It turned out negative?
Yeah.
Negative what?
Same as space negative.
Pi dy. We're doing dy's. We're doing dy. You know why? You know why? Because then this is saying that we are revolving around x equal to 2. Maybe? No. Would it be because what I'm doing is I'm revolving around x equal to 2 instead? And if we do that, we'll be going. Okay, all right. In any case, why would it? That's something to think about. We're done. That's it.